Yau inequality, and I'm really only doing surfaces. So S, the same as before, a surface, non-singular projective surface. So I want to assume, you know, let's just assume straight away that S is minimal of general type. So this means that k squared, k is nef, and k squared is positive. Then the theorem, the theorem is that C1 squared of S, this is k squared, is less than or equal to 3C2. So C2 is the Euler characteristic, topological Euler characteristic. And you know, if you want to think of this not in topological terms, but in terms of holomorphic algebraic geometry, C1 squared plus C2 over 12. This is the first Todd class, is chi of OS. So the same inequality says that C1 squared, k squared, less than 9 chi OS. So you know, for example, if I take C1 and C2 curves of general type, curves of genus greater than or equal to 2, as an exercise you can calculate k squared. So it's something like 2g1 minus 2 times 2g2 minus 2. And you can also calculate the Euler characteristic. So that's one. Anyway, you'll find that this is equal to 8 chi of OX. So this corresponds to C1 squared equals 2C2. So it's, you know, if you just want to see some examples up to 2C2, it's not so very difficult, right? It's known that C1 squared equals 3C2 only if and only if S is a quotient of the holomorphic ball. So the holomorphic ball means Z1 squared plus Z2 squared less than 1. So this is a domain with a lot of symmetry and so on by a compact group, by a co-compact group. So there's been a lot of recent progress about this, but you have to ask Kom Jong Hae if you want to hear this. Right. So the case going up to 3C2 or going up to 9 chi certainly happens. Right. So around 1975. Bogomolov proved C1 squared minus 4C2 is less than 0. So that's more or less by the arguments I've been talking about. I'll illustrate this proof, and then 1976. Mioka in algebraic geometry, and Yau in Kähler geometry. Proved C1 squared less than 3C2. So there are some higher dimensional generalizations, but they still involve the ratio between C1 squared times multiples of high plane section and 3C2 times multiples the height plane section. So this is really a result that is fundamentally to do with surfaces. So I'm going to mainly explain this point, and then I'm just going to say a few words about this point. So, for example, the you know, C, for example, Bart Peters, Bart Hulek Peters, Van der Ven, page somewhere on there. I think it's so Miocque's argument is really just an adaptation of Bogomolov's argument. It's quite clever, but it's basically using the same ideas. So, you know, as you can see from the numbers here, we're talking about somewhere in here there's a rank 2 vector bundle on S. Right, so where are we going to find a rank 2 vector bundle from? Well, that's easy. So let's take omega 1 S, or tangent bundle to S. Okay, then C1 squared greater than 4C2 for either of these would imply instability, in the sense that, in the same sense I've had earlier. So there would be a line bundle L contained in, let's do omega 1, and then with some possible sheaf of ideals there times L of M, where L minus M is big. Right, but in this case, C1 of S is a C1 of this bundle. I'm sorry, that's wrong. It's normal to define C1 to be C1 of the tangent bundle. So let me have C1 of this omega 1S is the canonical bundle of S. This is L plus M. And we're assuming this is a subset of general type. And so the Ks is also big. So Ks is big, and L is 1/2 of L minus M plus 1/2 of L plus M is also big. Right, and so Bogomolov says if L is in omega 1 of S, then L can't be big. Right, and this is basically an argument of Castelnova, or Castelnova de Francis. I don't actually know what de Francis did for this, but in any case, the argument I'm just going to give comes from a correspondence between Castelnova and his buddy de Francis. So let me say what the argument is. The argument says if L is in omega 1 S and H naught of L is greater than or equal to 2, then L defines then L is orthogonal, perpendicular to a foliation of S that is a fibration. So this means a morphism. So let me so that's the essential point. So let me state this as a proposition. So I've got OS of L inside omega 1s, and suppose that H naught of OS of L is greater than or equal to 2, then there exists a homomorphism. There exists a morphism S to C a curve genus greater than or equal to 2, so that L is I want all the sections such that H naught of L is f up a star of V, some space, some subspace V inside H naught of omega 1 of C. Okay, so I've got at some point in this argument, I'm going to construct a morphism from a surface S to a curve C using these sections, right? And so here are the fibers of the morphism. And so this is S, this is C. There are the relative tangent bundle there, T of S over C. So these are the tangent bundle fiber. Parallel to the set of tangent fields on S parallel to the fiber, right? And there's omega 1 here, which you should think of as sort of going along there. It's dual to the tangent bundle to C, and there's corresponding to this sub bundle of S. There's a sub bundle omega 1 f up a star of omega 1 OC inside omega 1 S. I hope I've got this right. So going to omega 1 S over C. And so there's a dual sequence here. Tangent bundle, the perpendicular tangent bundle goes to tangent bundle to S, goes to the dual of this guy, the pullback of the D of TC. The pullback of, this is the map D, the differential of the map, this is f up star of TC. Yes? And so however many sections I have here, they all come from one single map to a curve. Right, so in particular, L can't be big. Right, and there's a similar argument saying also if H naught of OS of NL is greater than or equal to 2, similar conclusion. So let me leave this. Let me explain the first part before explaining the second. right? So this is a fundamental building block of algebraic surfaces. Castelnuovo was using it around 1900 in order to, because he was still concerned with establishing the classification of ruled and rational surfaces. So here we're using it in a slightly different context, and also a slightly bigger context, because here we're, so the omega 1 of S can have, the S could be complicated surface, could have lots and lots of different, Albanese maps and so on. Lots of different one forms, right? However, the statement is that if I've got several different one forms that are contained in a single line bundle, so they're all parallel to each other in some sense, then they define a foliation, so an integral subbundle of the tangent bundle, and this foliation is not just any old vector fields heading off in any old directions. They're parallel to a fibration of the surface over a curve, right? So if I've got a fibration of a surface over a curve, then I've got these are the tangent bundles to the fiber, and this is the differential of the map. Right? So in just the dual sequences, here is the omega 1s, here is the relative canonical class of the map, and here is so this is the canonical class of each fiber, and then the kernel of that is going to be this L. So then L is at least the generic point equal to this. So L is parallel to this. The subsheaf L contained in omega 1s is parallel to this subsheaf of the omega 1 corresponding to foliation, fibration. Right. So the proof is Castelnuovo's idea. So Castelnuovo says, well, let's take S1 and S2 contained in H0 of omega 1, and let's assume that S1 and S2 belong to, so the thing we're really assuming is that S1 wedge S2 is 0. Right? So this is this is a free sheaf of rank 2. So locally it looks like O plus O. So I've got these two guys, S1 and S2. It's like having two vectors in a vector space. And what we're assuming is at the general point, these two vectors are parallel. So these two vectors are linearly dependent at the general point. So this means S1 and S2 contained in some line bundle L inside omega 1. Right? They're linearly dependent at every point. Or if I take the generic point of the surface S, I have these two things. And so this means that S1 is equal to F times S2 with F rational function on S. Right, they're both sections of one line bundle. So the line bundle at the general point is isomorphic to OS, and so take one of these as a basis of that OS, and then the second element has to be a multiple of it. Right. Now we have to say this, that there's the holomorphic D map. So it takes D from omega 1 to omega 2. Now this is all holomorphic. So this is this is type 1, 0 and type 2, 0 in right. So if S1 and S2 are global sections, global one forms, then ds1 equals ds2 equals 0. Okay, so I'm not quite sure how I should explain this, because I don't really understand the differential geometry involved here. but one explanation is to say, so the S1 is a holomorphic 1 form, so when I do ds1 is a holomorphic 2 form, is a type 2-0 form, right? But then there's some kind of argument that looks like this. Let's take ds1 wedge ds1 bar, right? And on the one hand, this is positive definite. So if S1 is not 0, if ds1 is not 0, this is positive definite. Right, so it's an element of omega 2 wedge 2-0 cross 2-0. So this is a 2-2 form, and possibly up to choosing some kind of orientation or something. This is positive definite. On the other hand, if you take its integral is 0 by Stokes' theorem. Right. So look, there's not much point in my trying to explain this because I don't understand it any better myself. Right. This is a general property of global holomorphic differential forms on a compact manifold. But I'm not pretending to give a proper explanation of it. So you know, this is if you look at this book, these guys sort of just refer back to an earlier lemma. So anyway, this is you just have to accept this as a fact. How do I want to see it? Maybe you understand this kind of stuff better. Yes, it's perfect, except that it would take me half an hour to spell it out. Okay, so what? So let's look at the map. I'm looking at this correspondence like this. So the f is a rational function, right? But I can still take d of f, and I claim that this implies the thing I just said here implies that df wedge s2 equals 0, right? Because I just calculate ds1, that's the same as df wedge s2 plus f wedge ds2. These two guys are 0. And so this means that also df is in the this L. Right. So again, this only works at the general point, but there's some open set where the L is. So there's this. You know, there are the guys that are vertical here. There are the guys that evaluate to 0 as relative differentials, and the thing we've got is that the f belongs to these. Okay, I should say this. So f is a rational function. So it defines a rational map. A rational map S to C. But then ds1 and ds2 are rational multiples of df, right? So you know, essentially the f here is now a rational function on C. Yeah, okay, I should say I'm taking S, I'm using it. I'm using the function f to define a map to P1, right? And then I'm just defining C to be the integral closure of S in this at the integral closure of P1 in the function field of S. So by construction, the F is just a coordinate here, right? However, the S1 and the S2 are regular differentials here, and they're parallel to the F, right? So they're just rational multiples of the F, and that means they come from S. Yeah, so there's sort of some T1, T2 here. These are in omega 1 of C, and the S1 is so. And now, so this implies that C, the genus of C, is greater than. Well, if there are any holomorphic differentials at all, then the genus of C must be at least 1. But in fact, if there are two different ones, the genus must be greater than or equal to 2. Right? And then a rational map to a curve of genus greater than 2 has to be a morphism. So that's somebody's theorem. I've forgotten. What's it called? Anyway, a rational map to a curve of genus 2 is greater than a morphism. And then the S1 has to be, this is called phi. Phi is basically the same as F. Right? Phi is determined by F. And then the S1 is phi upper star of T1. And the S2 is phi upper star of T2. Right? So I repeat, I start off with a rational map from S to P1. Right? There is some integral closure of there. Maybe the original map was already integrally closed. But these are the given differentials S1 and S2 are just rational multiples of dF. Right? And that means they are of the form d of something coming from C. Right? And that means there are now regular differentials on C, so that this, well, you know, I mean, maybe we have to do a little bit more work to do this, but this is the idea. Right? And this, so, you know, if H naught of L, if H naught of L is bigger than this, so if this contains S1, S2, and then some other guys, S3 for example, then exactly the same map applies to these, and the S3 has to be pulled back by exactly the same map. Right? There's only one map with a given, which integrates a given foliation. Yes. So you know the foliation of S corresponding to L in omega 1, yes, is now integrable. Right. Is now integrable and parallel to a fibration. Right. So you know, maybe I should work. Maybe there's a little argument in local coordinates saying work on local coordinates x1, y1, and so on. I've got little x1, y1 here. And then this f is some function of here. Maybe it has a multiple fiber. I have to worry about multiple fibers. But you know, this is at the end of all that explanation, the result will be that there are these regular differentials on C, and the given any of the given sections I had, S1, S2, and any further ones I had, are pullbacks of regular differentials on C. So that this means this is a maximum number of line bundles of sections a line bundle in omega 1 can have is all the guys that can be pulled back from a given curve, given fibration of S over a curve. Right? And so now if this is really Bogomolov's trick, if now if L is in omega 1 and H naught of L to some power n is greater than or equal to 2, then there is still a morphism S to a curve, so that L is tangent to the, is L is L in omega 1 of S is perpendicular, orthogonal to the foliation of phi. Right. So, you know, this is not. This is my argument here was basically assuming that H naught of omega 1, assuming that I'm in H naught of omega 1. So, but the proof is so the argument is a reduction to the case n equals 1. Right, and the reduction is given S in L tensor n, make a cyclic covering. Make a cyclic cover. So in other words, you know, it's a general point of the surface. I'm just going to be setting Z to the n equals S. And then, you know, you have to, this is going to give a new surface, T n over S. Maybe you have to resolve singularities, etc. But the upshot will be that that the L in omega 1 there, there's an L primed, you know, L sub n inside omega 1 of Tn, and the S1 and the S2 and so on will come from there. Right. So this, you know, I appreciate that I'm not giving a completely correct argument here, but there is a little way of making a cyclic covering here. So I've got all of these. I've got several different sections of L tensor n. So I say let's take nth roots of each of those, and then there's a new surface up here in which these roots, these z's and so on, z1, z2 and so on, will become sections of, will become holomorphic 1 forms on this Tn. Right? So there's something to check here that I'm not doing properly. Right? But as I said, this is all in this. This is, you know, I have a little paper on this where the argument's written out correctly, and you know, all the other guys who followed on. I mean, you know, Bart Peters van der Ven. There's arguments of Eckhart Vivek and other people who did this much more carefully. Okay, so I recall. So Bogomolov says. So S, surface of general type, then C1 squared less than or equal to 4C2. So the proof was else, otherwise, there's one of these sequences, L goes to omega 1s to some sheaf, which some sheaf of ideals I don't really care about, times m, that we write at OS of m. Where this OS, where this L is big. And this contradicts, this is a contradiction. So again, you know, this is in some ways a really very coarse argument, right? The kind of instability you'd have in Bogomolov instability is this thing here is really sort of big in a very strong sense. This L minus m, some multiple of L minus m is bigger than any ample divisor. So I add on a little multiple of k, I'll find that some multiple of L is bigger than any ample divisor, right? Whereas this statement here says that if I've got a line bundle contained in omega 1 of S and it has any number of sections, any non-trivial number of sections, then necessarily that can only happen because they come from a curve. And so Miocca's proof, which I'm not going to be able to tell you properly about because I haven't had time to prepare it. Miocca's argument says basically we don't need such a big. We don't need L bigger than 1/2 k. It will be enough to get L bigger than epsilon k, right? Because so this argument here said L minus m is a big divisor and L plus m is ks, and so this means that L is bigger than half ks, right? However, if we have that L is even quite if L is any big divisor, it's still a contradiction. It's still the same contradiction, and so Miocca's argument, just explained quite roughly, is saying that if C1 squared is greater than 3C2, Miocca proves, well, I mean, we prove a contradiction. So if you're proving a contradiction, you can express a contradiction in many other ways. But in particular, he proves that chi of Sn of omega 1 tensor OS of minus alpha n ks grows like n squared. I'm sorry, grows like n cubed. Grows like n cubed. I should write as big O of n cubed, so it's greater than some positive constant times n cubed, where alpha is greater than a quarter, or maybe it's a third. I don't know. I haven't. Okay, so this is basically just Riemann-Roch. So in the you remember so I've had this argument now. I had this argument in a much simpler form when I talked about the index theorem, and I also had the same argument when I talked about the original Bogomolov thing. Remember, I'm writing Sn of omega 1 in the Bogomolov argument. This was times minus n over 2 times ks. Right, and the over 2 was the same as this over 2. Right, so you remember what we were doing here. What we're doing here is we're writing omega 1 is alpha plus beta, and then we're writing down the Riemann-Roch formula for this guy. So this is sum n minus p alpha. So this is, sorry, direct sum. N minus p alpha plus p beta. And then minus n over 2. Minus n over 2. Okay, and so this is something involving alpha squared minus alpha squared beta squared and alpha beta, and the point was this really something to do with alpha minus beta all squared. So this is looks like n squared. At the end, you get n cubed times alpha minus beta squared. Right? Just because I'm doing n minus n here, so I'm getting 1/2 of n minus p here, and then I'm getting p 1/2 minus the same thing. Right? So this is all, each of the terms here is just some multiple of alpha minus beta, and then it's summed over some range of values. So this was, this is the original Bogomolov argument. Right, but the same, you know, the sort of Miocca's argument is similar. It's basically the same calculation. So it's the same calculation, but just slightly different version of the right. And so this means that I can find a non-trivial map here from, so you know, after, so I can find this alpha n ks. I can choose the n such that alpha n is in Z. And then this alpha n OS of alpha n k embeds in Sn of omega 1. And then you continue the same argument, basically the same contradiction. So I'm sorry, I'm not really in a position to give the correct form of the argument. As I said, it's all in this book of Bartulik, Peters and van der Ven. I think I'm going to leave it at that for today. So next week, from next Tuesday onwards, we're doing this winter school at Chongpyeong, something like that. Chongpyeong. Chongpyeong. Pyeongchang. Okay. Yes. So and then the subject's really quite different. So. So I would like at some point to write this up in a very clean way, because I'm not very happy with the argument as it's written in this book. But I'll just have to leave it for today.
The paper is the same. It's quite a mess.
Yes.
It's correct, of course, but it's quite a mess.
It's correct. It's been checked by lots and lots of people, but that's not the same as saying that it's readable. So, you know, if you think about these sheaves, I'm writing down Sn omega 1 here, and then I'm writing down some number here, alpha, which is less than 1/2. And so, you know, when you do the you know, if this chi is big, it means either H0 or H2 is big. But in the Bogomolov argument, you took the H and H2 and you turned into H0, and you find H0 and H2 growing at the same size. So here the H0, of course, grows bigger than the H2. The H2, when you do the same duality arguments, because this alpha is less than 1/2, you get less, so it ought to be easier to get the result. Right? And then, so they argue, Miocca and these four Russers argue, you know, I don't know. They argue that you know, on the one hand, this sheaf has chi. On the other hand, this sheaf has H0 and H2 both equal 0, and the chi is growing, and that's a contradiction. But you know, that argument really conceals where the contradiction is coming from. The contradiction is coming from, you can put some reliable medium-sized power of the canonical bundle inside this Sn of omega 1. And so this means that on some covering surface, the sum covering surface up there, or I can actually take a single multiple of K of an ample bundle and put him inside the omega 1 of the surface. That's contradiction. So the contradiction ought to be much clearer than that. It ought to be much coarser. So it's an interesting thing that this argument of Mioka, really uses C1 squared greater than 3C2. So in the limiting case, this argument on its own does not give any conclusion at all. C1 squared is equal to 3C2. As it stands, this argument gives nothing at all. So over a period of about 5 years, Mioka found some clever way of arguing on writing down log versions of the canonical of these sheaves if there are, for example, -2 curves, right? And so if there are -2 curves, we now have this result with orbifold Chern numbers and so on, and so some of these cases are. So in particular, there are now Mioka has purely algebraic proofs of the result when Ks is not ample. So that if C1 squared is equal to 3C2, then necessarily Ks is ample. So this was proved. That was proved by the differential geometers, by the Yao and his followers, but not by Bogomolov Mioka till much later. Anyway, so I'll be as is written here. I'll be giving 2 talks later in March after this school. But they'll be on different topics. I'll be independent of the talks I've given so far.